talking about kinetics this week, and we want to figure out how fast reactions are. And there are really a couple of reasons why we want to do that. There is the obvious one. We want to predict how fast the reaction will run to completion. We want to know what the concentration of reactant XYZ is at any given time. That is a very valid reason. There's also, however, a point that we might want to learn something about the chemistry which we are doing. How do the reactions depend on the reactants that we have? What is involved, what isn't involved? Are there many steps in the reaction? What is a bottleneck step? Which is a fast step? Which is a rate determining step? Which is a slow step? How many molecules are involved in the reaction? So that is also a valid reason to look at kinetics, not because we're interested how fast the reaction is per se, but figuring out how the rate of a reaction depends on the concentration of reactants can teach us something about the chemistry. And finally, there is another reason why we might want to look at the kinetics, and that is, in textbooks, there's always only one reaction which is going on, but in reality, there are many competing reactions. And if we have many competing reactions, then they will result in the different reaction products, and only one or a subset of them might be desirable products. And so, figuring out how fast the reaction goes towards the desirable and towards the undesirable products will tell us how much at the end we will have desirable and the undesirable product. We want to create make the reaction go more towards the desirable products, and for that we need to study the kinetics of that possible reaction and also the other possible reactions to the non-desirable products, and see how we can inhibit some of them, their rate, and how we can accelerate the rate of the others. So there are many different reasons why we want to study kinetics and what kind of information we get out of kinetics. But in all cases, we define something which is the analogy of speed or velocity of the reaction. And that can be called just the rate of the reaction. And if we talk about the rate of the reaction, it's the strangely normalized beast that we looked at the last time, where we always divide by the stoichiometric coefficients. And as a consequence, it depends on how we write the reaction. The rate of the reaction would be different if we divided a 2 out of all of these ones, because then there's a 2 divided out of all of these ones here. And so, even though the chemistry might look the same, but the rate will be different. But then I can also look at the rate of consumption of something, or the rate of production or formation of something, and they are not normalized. And it's always good to keep in mind which one of those ones we are thinking about. Last time, we looked at the unimolecular reaction, a reaction that involves only one molecule as a reactant. And then we realized from a unimolecular reaction, and the fact that the molecule doesn't know how old it is, it has no watch to look it up, or calendar to look it up, it just is. So a molecule doesn't know how old it is, and as a consequence, it has every single time unit the same likelihood to decay as it had the previous and will have the next one if it doesn't decay. And so we find that the rate of the unimolecular reaction, how much change of the concentration of A we have per unit time divided by, for unimolecular reaction, this is of course a 1 over 1, and with the minus sign in front, because it decomposes and we want to get a positive number, the minus cancels the minus in exchange of the concentration. That is the rate, and we found that depends just on how many molecules we had in the first place. If we have twice as many molecules, we have twice as many of them which will decay per unit time, because every single molecule has the same likelihood to decay per unit time. And then there's a rate constant K in front of it, which tells us what the unit of time is, how many molecules decay, what's the probability that it decays per unit of time. And then the whole thing goes to the power of 1 over here, so you usually forget it. But technically, we can now say, okay, this goes to the power of 1 here, and so the order of that reaction is 1. It could go to a different power over there, and we would have a different order. And we're going to talk about more difficult orders on Wednesday, but today it's still too complicated. Then we look at a reversible reaction. The reaction can go forward and backward. Something like this one here, where the blue one reacts to the green one, but as soon as we have some green, the green can also be reacted back to the blue one. So if we have such a reaction, we will eventually get an equilibrium. At some point, the forward and the backward reaction will have the same speed, with the same rate. And if I want to know what is the change of the concentration of A over here, then I can get that out relatively easily. I can say, okay, the change of the concentration of A per unit of time, don't need to normalize it because here the A is 1, so it's 1 over 1 here in front. I don't need to worry about that. And then I have change of the concentration of A for the forward reaction will be negative. I will get less A, so the change is a negative number. So it's a minus sign. The rate constant for the forward reaction. And if this is a unimolecular reaction, if it's only one molecule reacting by itself, then it goes by the concentration of A. But then there's also the backward reaction possible, and if we know that the backward reaction is also a unimolecular reaction, which is not a given, just assumed over here. But if we assume that the backward reaction is also a unimolecular reaction, then that backward reaction affects the change of the concentration of A, which is positive. More A will be there if C decomposes into A, and it goes by the concentration of C times whatever the rate constant for the backward reaction. Okay. Now, if I have something like this, then I can go about that in 2 ways. I can figure out what is going on here. I can integrate this rate equation, or I can, maybe I can find somebody who did it already for me, and look it up what the integration rate equation is. And the third way is I just type it into Excel and have Excel. And you can probably guess, I find the most useful way, the one where we say we'll just type it into Excel and do it. But of course there might be different ways for doing it. Let me first show you how I think you would just do that by typing it into Excel, because that really is the most useful way, because what we'll find out on Wednesday is that if I have second order reactions, most of them I can't integrate anyway, so I need to find a way to do it. So it would be good to do that this way. So let's have a look at this one. And I have an initial concentration for A, and maybe I want to write my initial concentration for A here, and maybe my initial concentration for A is 0.1 mole, and I like calling things by name, so that is A0. And then I might also have an initial concentration of C. Could have had some starting concentration of C as well, after all. And if that were the case, then that would be maybe 0.02 or so, and I'll give that a name as well. That would be okay. Now, I need to know the rate constants. So my K forward over here let me choose the same rate constants as we will have in the homework, at least by the numbers. That is also 0.1 and 0.02 over here. So that way, so 0.1 and get backward is 0.02. Same thing as over there. Doesn't need to be the same thing, but let's assume this one for now. You can always change it. Then I have here LB of underscore forward and get back. I need, okay, if I set up my Excel table in this way, I told you much earlier, I always like having an index. So let's make an index. My index starts at 0, of course that's the way to do it, and then, okay, that's just 30 index. Then I can, from the index, create the time in which we work. So maybe I want to have a time step defined, which is maybe 0.1 seconds. Every 1.1 second, I want to make my calculation. So the time is then my index times my time step. And that's what I have over here. So here I have my time. The next thing which I want to do is that I might be interested in the concentration of A. Now the concentration of A, which I have initially, that is of course my initial concentration of A. And then I have the concentration of C, and my initial concentration of C, that is of course here. And now I can figure out what is the A. What is the change of the concentration? Well, the change of the concentration A, change of the concentration A. Change of the concentration of A is right here, correct? So that is minus. And I need to multiply everything at the end with t, of course, so to get, because I want dA, not dA by dt. So I need to multiply dA over here. So if I'm doing this, I'm opening parentheses so that I can put dt at the end. And now the k forward times the concentration of A, the concentration of A is here, plus the k backward times the concentration of C, correct? Times the concentration of C. And now I need to multiply it by dt, and that dt is my time step. How fast I go, what step of time I'm doing. And then I'm getting this one here as a change of my concentration, right? Now, what is the change of the concentration of C? For every A I make, there is one C being produced. So there are many ways of figuring out what the change of the concentration of C is. The easiest one in this case, and not universally the way to do it, but the easiest one this way is just to say it's minus dA, because for every A I'm losing, I'm making C, so the change of the concentration of A needs to be the opposite of the change of the concentration of C, because the one is converted into the other. Now after my time then, I have a concentration A here, which is this concentration here, and I need to add this, the change, which is a negative number, so it's actually going down. Okay, I need to do the same thing over here, which I did. And now for these ones here, I can just say, do it this way, that they are now referencing the numbers in this row, so that it works. And now I'm essentially done. Now I can just say, oh, keep doing it. And I can figure out right away what is my concentration of A. Yeah, that is my concentration of A as a function of time. Right away, I got it. And if I'm interested in what is the concentration of C, then I can just insert that into my A. So I'm interested in C and the X value is of course the time, and the Y values are the values for C. And where did it go once? Something very well. I didn't select it. Values are in E's. No, X values are not in E's. X values. Okay, here you go. So, you can look at graph and you can see right away what the result then is. So that is how we have Excel do it. What we find over here is that if we add the legend here, then A is going down, very low value over here, C is going up, fairly high value over here. Will it go all the way? If I were to look for a longer time. Now, if I want to look at a longer time for this one, then I can just change, of course, my timing. So if I were to say put now 3, so then I'm going for the time, and now I'm going to like 100 seconds over here. And is it really at 0? Is this really at 0? It seems to be kind of getting to a fixed value. This was my A, this was my C. So if I go down here, and you can see this is the A, this is the C. particular value over here, A. They don't seem to go all the way to 0 for A. So it seems there's an equilibrium. Maybe that equilibrium depends a little bit on how the rate constants work. If I have the same rate constants for both reactions, then what you find is that, oh, something else is happening over here. They didn't even come to any conclusion in the time. They are now both very slow. If they're both very slow, maybe I need a time step a little bit faster. Even faster time step. So that I see what's going on. Even faster time step. Now there's 3 seconds. And you'll find at the end they come all to the same concentration. Now that makes a ton of sense, doesn't it? If I have a forward and a backward reaction being the same rate, the same speed, then if I wait long enough, I'll have the same amount of A and B because only then the concentration will cancel, correct? If I make one rate constant exactly twice as big by that logic, then I will get a 2-to-1 ratio of the particles. I will have, if the forward reaction is twice as fast, I will have only half as much A. But I will have twice as much C. Because only then I get into equilibrium and I have a state in which the forward and the backward reaction have the same rate. So what I'm doing in the beginning over here, that only changes how much my initial concentrations are. That only changes in the initial phase over here, in the initialization of your reaction, what is going on. Ultimately, you're getting to an equilibrium. And that equilibrium is not determined by whether you have A or C in the beginning, but that equilibrium is determined by how fast are the rate constants. And if the rate constants are fast, the same rate, then it will always be the same thing if I have the same concentrations for them. And otherwise, you can see how they can just equilibrate. Does this make sense? Anybody having a problem with this? This is how kinetics works. And I think it's really nice to show that in Excel in this way. But of course, one could say, oh, that's really not what I want. What I really want to have is the solution, something I can write on paper and then do that kind of things. And of course, one can do that. So let's see that we have that over here. Now we have this equation. How on earth can I integrate that equation over here? How can I integrate this rate equation? That's really what I need to do, correct? And we need to figure out what's the concentration of A at the function of time, and then by integrating this rate equation. So how do I do that? Well, the only way how to do it is separation of variables, correct? So I have my dA on the left-hand side, and then on the right-hand side, I have minus K forward times the concentration of A plus K backward times the concentration of C, the whole thing multiplied by dt. Same thing actually what I did in the Excel. But now I start having a problem. My concentration of C here is kind of a rogue variable, something where there is kind of A included in it, but not really. And so I need to realize that if I have initially that amount of A and that amount of C, then at any time the sum of the concentrations will still be the same. If I add up the concentration of A and C, that's the total stuff I have in there, and that is the same as the concentration of A and C at any other point in time. I'm not making new species in that sense. So my concentration for C is the concentration I had initially plus the concentration C I had initially minus the concentration of A, correct? No. That's what I can put in here, correct? So I have minus K forward times the concentration of A plus K backward times A here. So it's really minus K backward times the concentration of A. And then I have still K backward times the concentration of A I had initially and the concentration of C I had initially. And the whole thing is still to be multiplied by E. Okay. So I can then kind of trivially say this here is minus K forward plus K backward times the concentration of A, that is these two, plus K backward times the concentration of A I had initially plus the concentration of C initially, and the whole thing needs to go still with my dt. Okay, but separation of variables is all about putting everything which was A on the other side. So everything with A really needs to go on the left-hand side. So I have dA in the numerator, and then I have in the denominator the concentration K forward plus K backward times the concentration of A plus K backward times the concentration of A plus the concentration of C. And that is dt. Okay. I don't like to have anything in front of my concentration of A over here. So I divide this one here out. Well, really, I multiply the whole thing, whichever way you want to call it. What I'm doing over here then is that d of the concentration of A is concentration of A times plus K Boltzmann over K forward, K backward plus K forward with a minus sign here times the concentration A plus the concentration of C. And this gives me over here the minus K forward plus K backward dt. So I multiplied on both sides, this K forward minus K forward plus K backward. I have it here, it cancels with this one, and then up here I need to divide it here, so I have it like this. And yes, so now I have my dA and something over here. So now I can almost integrate it. I don't know whether how you like doing your integrations. there are a ton of different ways, of course, how you can possibly do that. But for me, it would be, for instance, one way of saying I could say maybe X is the concentration of A plus minus K backward divided by K forward plus K backward times the concentration of A plus the concentration of C. Okay, if I have this, then I can ask what is dx by dA, and dx by dA, is this depend on 0? That doesn't have a factor, so dx by dA is only 1. Okay, now that becomes easy. So dx is the same thing as dA. Okay, so then this one here becomes dx over x equals minus K forward plus K backward dt. If I substitute this one here for this one and this one here, I'm getting here. Okay, this one here I can integrate. So that is ln x minus ln of x0, and this one over here is minus K forward plus K backward of t minus t0, if I integrate. Okay, if I'm doing this one here, then I can now put it all on the exponentials. Then if I put that on the exponential over here, I find this is x divided by x0, e to the power of ln x. X e to the power of minus ln. This one is 1 over x, so x over ln x equals e to the power of minus K forward plus K backward times t minus the starting. Okay, that means x equals x naught e to the power of minus K forward plus K backward times t minus t naught. Okay, then what is x naught over here? Now, we know what x is up there, right? We still have it up there. X was that. So we have then for this one here, up, X was the concentration of A plus minus K forward over K forward plus K backward times the initial concentrations of the two reactants. That is my X. And this is my X naught here. My X naught is again, so equals the initial concentration of A, because it's X naught, it's initial concentration, plus K minus K backward over K forward plus K backward times this. And then the X naught is also multiplied with e to the power of minus. Okay, forward plus, okay, backward times t minus the initial time. That's kind of a lengthy thing, isn't it? But, so finally, my A is, this is a minus sign over here, right? Plus times minus. So if I bring it over to the other side, it will be plus. It is k forward over k forward plus k. Wait, that was k back. So straight back over k forward plus k backward times this. Now I'll go at this one to the other side. Okay, and now I have over here a plus initial concentration minus, that's that minus sign here, k backward over k forward plus k backward times the initial concentrations times my E factor minus k forward plus k backward times T minus. Okay, so that's the result. Wasn't it nice in doing that in Excel? But this formula is actually nice. Because let us just assume for one moment that we now go to time infinity. We wait forever. We wait forever. T minus T naught becomes infinite. E to the power of minus infinite becomes 0. This one falls away. So we know that if I'm going to infinite time, this one here will be my equilibrium concentration. So I can call this maybe here a equilibrium as well. If I wait forever, that's where I will be. Because this here will be 0, and then 0 times that one be at 0. And then, if I'm looking at my equation again, then I can see that the concentration for A is the equilibrium concentration plus how far away are we from the equilibrium concentration? Because this one here I can also write as the concentration of A I had initially minus the equilibrium concentration. Because this one is the same thing as that. Times now e to the power of minus k forward plus k backward times t minus t0. So how far away, how much out of equilibrium I was, the difference between the concentration I had of A in the beginning and the equilibrium concentration, and that difference over here, that decays with the rate, which is the sum of the two rate constants. It's an exponential decay over here, and what goes over here away is my initial variation from the equilibrium. Now we can go back at what we had in Excel. And that's pretty much what was going on over here, right? If this one here was my initial concentration, then it was so and so much away from the equilibrium. The difference between the two was this one here. And then I have an exponential decay of this variation from the equilibrium. That is what you find in Excel a lot. So what we can do, of course, now is we can type this formula into Excel. We could say, okay, we can say, okay, we want to have a concentration of very, very long formula which I have over here. And I'm not going to do that right now. I think you can imagine that. And you'll find that concentration will then look just as much as what I calculated here in Excel. But you can figure out how you will just plot that by typing into Excel. Here now the formula for that was something like k backward divided by k forward plus k backward times the initial concentration, and so on and so forth. You could type it in there, and then you can plot it. So, what would you do for the concentration of C naturally? How would we get that? Anybody an idea? How would we get the concentration of C? Now there are a couple of different ways. What was written over here, we can realize, oh, the concentration of A, the concentration of A plus the concentration of C has to be the same as the initial concentration of A plus the initial concentration of C. So now we just got a formula for the concentration of A, got a formula for the concentration of A over here, plot my formula for the concentration of A in here, and then I can derive the formula for the concentration of C. That's one way of doing it. The other way is to say symmetry. If I had started out not with A, but with C, let's switch around everything. Kb becomes Kf, concentration of A becomes concentration of C. So this one here, Kb becomes K forward. This one switches and this one switches, but it doesn't make a difference because they're still added. This one and this one switch, but it doesn't make a difference because they are added. This one over here becomes concentration of C. Then this one switches, here it doesn't matter, here it doesn't matter, here it doesn't matter. So you could also directly find the formula that if it's so symmetric, forward or backward, during the reaction, you can just switch things up in your calculation. Whichever way you do it, you can get that formula. Okay, now if we have that, we solve this one. If you have competing reactions, like I'm showing here, A can go to C and A can also go to D. The rate constants are slightly different between those two reactions. Then you can do the math relatively straightforward as well. For the concentration of A, it goes the fastest. For the concentration of A, you can set up the rate equation right away. For the concentration of A, you know that the concentration of A, the change of the concentration of A over time is you losing something to the first reaction, and that is K1 times the concentration of A, and you're losing something to the second reaction, it's K2 times the concentration of A, if both of them are first order. If both of them are first order reactions. First order reaction towards this, first order reaction towards that. Now this one here is of course just minus K1 plus K2 over here times the concentration of A, and then it's just another K, and so you get an exponential decay as you find over here with the sum of those two rate constants. For the other ones, if you want to know what is the concentration of C over time, then you figure out that the change of the concentration of C per unit time, that is positive now with the first rate constant times the concentration of A. And the concentration of A, you know what the concentration of A is. That's this one. A0 times E. So now you have an E function here on the right-hand side, and you can do your integration with an E function on the right-hand side, and you come to the formulas which are given. Finally, we can have consecutive reactions. We can have A becomes B, and from B it becomes C. And you can do the same kind of stuff again, and you get results there, but that's really your homework. So for the first order consecutive reactions, assume initial concentrations of A, and B and C are nothing. Assume rate constants of 0.1 and 0.02 Hertz for first and second reaction, respectively. Make an Excel file, just the way I made my Excel file in the beginning. And then do the math analytically. Derive the formula which you have over here. Derive this formula over here. And then plot that formula as well. Most chemistry books will tell you how to derive that formula. It's just cumbersome maths, but it's very doable problem. So get a taste for what is easier, doing it in Excel or doing it in. Thanks so much.